Okay, perfect. Yeah. So thanks everyone for joining. And this is the last session in our quantum error correction tutorial series. And in this final session, Andrew will continue on fault tolerance, and he will, take us along, like discussing that paper by Daniel Gottsman from 2014, 13 something. And yeah, so Andrew, please start. Yeah.
Yep. Uh, all right. Yeah, I'm just gonna continue like the rest of the stuff that we haven't managed to cover last time on that constant space overhead um fault tolerant protocol. Yeah, so last week we went through like the descriptions and the ingredients of the protocol, and we went through a couple stuff, the QLDPC code that is used in the protocol, and the Shore quantum error correction protocol that's used in the for the fault tolerance scheme, and we talk about threshold theorem and part of the proof. And so today I'm just gonna go through the rest of the proof and also explain how logical gates and logical measurements and preparations are implemented in this scheme. And yeah, so that will and then that will give us the rest of the proof, and lastly just do the overhead analysis just to show you that it's we only have a constant space overhead. Yeah, so just a quick review from last week. So instead of doing concatenation, which is kind of like correspond to this, sorry, let me just pull up my console. Yeah, so instead of doing this concatenated code where you have multiple layers of codes, and then like uh, the qubits, the physical qubits of the top layer is the logical qubits of the next layer, and so on and so forth. But instead, we're doing like this block concatenation. So I have like this what's this, 1, 2, 3, 4, 5, 6, 7, 8, like 16 qubit codes that encodes 3 logical qubits. So instead, I'm just gonna use 4 of them to encode this 12 logical qubits. Yeah, and like these are the components. So we block encode our logical qubits to QLDPC codes, and we have a sequential circuit. So we only do one gate at any given time, or any other logical operation. And then we do error correction over bunch of over this block, so we can reuse the ancillas. And the error correction style that we use is this Shore error correction. And to implement the gates, we're gonna use this nil teleportation. Um, and yeah, we want to ensure like this local stochastic noise stuff later on. Yeah, yeah, we're gonna use this quantum LDPC code. So to just remind you of the notation, so an RC LDPC code means that um, each stabilizer generators only acts on at most R qubits, and each qubit is involved in at most C stabilizers. Um, and we want our code to have a non-zero asymptotic rate and a distance that goes to infinity as we take in this code family. And we want this particular growth of the number of physical qubits. Oh yeah, and lastly, we want the logical error rate. There exists some decoding procedure such that the logical error rate um, you know is, is bounded by this. Yeah, so this is one key theorem that we want to use in the proof. So if our QLDPC code satisfy these 4 conditions, then the logical error rate is going to be that. Basically, it's suppressed exponentially in the distance of the code. and the residual error, in this um, stochastic model is that. So for every qubit at the output, the error is only going to be p0 over 3, right? So p0 is this threshold on the initial error rate, and we have this data error rate and bit flip error rate, syndrome error rate. Yeah, so just a little bit on the Shore QEC. I'm not gonna go through line by line here because we covered this last week. So basically, we want to prepare this cat state as an ancilla to do the syndrome measurement. So this is just way to Z check. And then you do this control Z and then a layer of Hadamard, and then you measure each of the ancilla qubits and just take the parity. Um, yeah. So the size of this cat qubit is going to depend on the weight of your check. So it's mostly R, right? Because we are using this QLBC code. Yeah, this is a very long threshold theorem. I'm gonna show this again later on to kind of like go part by part as we prove parts of it. But the point here is that we have this threshold PT such that if the physical or um, local stochastic error rate P is below PT, then I can construct this um, simulation circuit C tilde that simulates the C um, using this number of physical qubits um, with statistical distance epsilon. So it's kind of like the output distribution is close to C. Yeah, and I'm gonna go all like through these like over other like overheads and stuff later on. Right. So this is still kind of like review. So this is like the last condition that we want from our LDPC code. So yeah, we want this like this thresholds on data qubit initialization and syndrome bits. And we want to repeat the syndrome measurements for the decoding process because we can have syndrome bit flip errors. Yeah, and these are the thresholds again. And yeah, if we want the code to satisfy, or there exists some decoders such that if the decoder is successful, then the residual error is bounded by this number. Yeah. Um, okay, so these are the basic um, error model versus the simplified error model. So basic error model is this local stochastic. So I've this probability of having errors in k locations is bounded by this p to the k. Um, Whereas in the simplified model, I have three different errors, right? This initialization error, which is basically kind of like happens before my QEC round starts, and then data error, this PD, which kind of like happens, like there, and then like propagate to the to after the QC round, and then like the syndrome bit flip error Q. Um, yeah, so basically like the point on this slide is that I want to partition my code, right? So if I have k qubits in my original circuit have k qubits, then I want to partition that, to this different blocks of LDPC codes. Um, And yeah, so we start with this local stochastic model. And then I think we went through part of this last week. So we want to map the local stochastic model to the simplified model, right? To this P tilde, PD, and Q. Um, and yeah, okay. So I guess like um, so here we want to map this stochastic local stochastic noise to this bit flip errors and physical physical qubit errors, and that could come from errors in the ancilla preparation. Like this is the cat state preparation circuit, and that could propagate to this data qubits, right? So that will be like this P sub P. And the gates themselves could be there could be they could fail, and they could cause more data qubit errors. Um, and also we have like this waiting time because we only um, do error correction on parts on some of the blocks, but not all of them, to kind of like reuse this ancillus. Um, and then yeah, that could also contribute to the data error. Um, Yeah, so putting all those three together, we did cover this last week, so this is just a quick review. So since we do this post-selection on the cat state preparation, so we have this 1 over PA, 1 over 1 minus PA factor. And we use C ancillus per qubit because we use QLDPC code, and A is the number of fault locations in the cat state circuit, preparation circuit, and P is the local stochastic error rate. So we get this first term, and then we have this less than C controlled Pauli gates, right? Because you see here, like so the number of gates here depends on the weight of the stabilizer you're measuring. So it's bounded by CP. And then we also, yeah, so single syndrome measurement has L time steps, but, we only do that, every S cycles because we further partition these blocks. So wait time error is SLP, right? So um, the um, physical qubit errors um, is this equation one. Um, Oh yeah, because like the Shor syndrome extraction is fault tolerant, so the probability of me having a data errors inside that syndrome extraction circuit is bounded by this PP to the A. Yeah, so this is where we left off last week. Um, so um, so we calculate now. We now want to calculate this bit flip error on the syndromes. Um, so the first source is this cat state preparations. So that could propagate to the to like like the ancilla wires. And so similar to the data qubit analysis, like we did post selection, and there are a locations inside the circuit. So we have this first term, and we have this gates, right? And R is the like that the number of the size of the stabilizers, the maximum size of a stabilizer. So like um, yeah, you see like the controlled Pauli's and Hadamard's and measurements are equal to the number of the weight of the measurements. So that's what we get. So yeah, so we now okay, so because we do like this okay, so we have at most C syndrome measurements or checks, right, for every qubit because we have this QLDPC code. Now, so this is kind of like just kind of like a trick and doing the accounting of like how many faults or errors that we have. So okay, so say C is equal to 5, and I have like this stabilizers on like some qubit with maximum degree. So the way that we want to assign where the error goes um, is that okay, so if I have some error on this first G0 so first circuit that measures this G0, then like every syndrome the syndrome of G0 and every syndrome after that already takes into account that errors that have that error that which happens G0. So it's kind of like it's really not a bit flip because it's kind of like the syndrome is kind of like out of the actual errors that is in G0. But if I have like something like a fault that happens in the middle, so the entire syndrome here are kind of like not consistent, right? So this first, we could consider this first to be bit flip errors, or yeah, bit flip errors. Because like yeah, kind of like this faults that happens in the middle. So everything after that is kind of like consistent. It kind of like records detects that error, but whatever before that did not. Yeah. Um, okay, so basically like what like the upshot here is that the maximum number of syndrome bit flip that that rises from any fault is bounded by C over 2. Because we need to use that in this next step to count the bit flip errors. So okay, so yeah, so this is basically what I showed you in the previous slide. So each physical error inside this syndrome extraction circuit can cause at most C over 2 errors. So if I have like this set S that contains BD data errors and BB syndrome errors in the simplified error model, so I have like, like BD errors there and BB errors there. Um, so I can like I can bound that by that. Um, and so the reason is that because like the syndrome errors can come from like an actual errors in the measurement, like this guy, or from some, like physical data error, like somewhere that caused the bit to flip. Um, right. So that the bit flip errors that came from like this actual data errors, so I multiply that by C over 2 because like that's the maximum that each data error can cause bit flip errors. And I have this AB actual syndrome errors, right? But now I have to subtract that out, subtract those that are caused by data errors, right? So that's why the number of syndrome errors is this actual measurement error plus data errors. Um, yeah, so right, so that's basically what we get. And so this number AB, so it only falls in this interval. Yeah, and that's because yeah, probably I should not just yeah, I shouldn't. I don't think I want to go through the details. There's still a long way to go. But yeah, so basically like you can kind of like bound this um um value AB um so that now we can bound the probability of errors on the locations in the set S. Like you have to do like some combinatorics here because the data error probability is different from like the actual measurement error probability. So you want to take these into account. Um, and kind of like use like all the possible values of AB to kind of like sum over this um so that come up with this value. Yeah, don't worry too much about the like the arithmetic. Not going to go through that in detail, but basically like we want to yeah, so that's what we have obtained. And so yeah, we want the errors to be local stochastic. Um, so we want this probability to be bounded by that, right? So we want this value, like this PP and PB. We want those the values of PP and PB such that this kind of works. Um, yeah, so we can use like this, like this all possible values of AB here, like this guy, um, and kind of like plug that in here. So now like this is kind of like the bound that we need to satisfy. And yeah, after like just working things out, so these are the values of PD and Q that works. Um, so that this equation 5 is satisfied. Um, so now we can just choose like this kind of like threshold for data errors and threshold for bit flip errors, this P1 and P2. Um, to that upper bounds this PD and Q. Um, yeah, so that's kind of like so now we've taken care of this like this thresholds for data errors and thresholds for bit flip errors in this simplified model, but now we're left with this p tilde. So this is so to kind of like analyze this p tilde and put a threshold bound on it, we need to look at errors that comes from gates, logical gates, or other logical operations. Because like like this p sorry, so I guess like this dotted line should be there. Um, uh, yeah, um, or not actually. Yeah, because like before this speed tilde, there could be like some like some big gadget like that implements some logical gate, and there could be error there. So we need to talk about how we implement those logical gates. Okay, so the gate implementation here is using this like this nil style teleportation, which was proposed by Nil. Sorry, I can't remember what his first name is. Um, but yeah, that was like over 20 years ago. And basically this will allow you to do like just any gate that you
I
want.
mean, like Emmanuel Nil.
Yes, exactly. Yes, thanks. Yeah, so basically like this protocol, yeah, and also like Gutzman and Isaac Trong like proposed like this kind of like scheme back in 99, where you can do like this universal computation, fault tolerant computation using this teleportation kind of implementation of logical gates. But yeah, but the idea is that now you kind of you want to prepare this um, ancilla which encode the gate that you want to do in your data in your system, this U bar. So basically like you prepare okay, so if my code block is this has this parameter, so it encodes like this um ki um um logical qubits. So I want to prepare like this logical Bell state over two blocks, right? So I have like this guy. Um, and then I want to couple one of those blocks with the actual data block of my where I do my computation. And then well, basically like this entire procedure is basically I'm doing this transversal Bell measurement. So I couple each of the physical qubits, and then I do this Hadamard, and then I just do this single qubit Z measurements. And then what that does effectively is that I'm going to implement this U bar on this psi bar. but now it's switched to this one of the ancilla systems. And depending on the measurement outcome, I'm gonna have some correction that I need to do. So if I just want, if this U bar is a logical Clifford, then this correction is just gonna be Pauli. But if it's a non-Clifford, so if it's something from the third level of Clifford hierarchy, such as the T gate, now the correction that I need to do is I need to apply a logical Clifford again, and then I need to do like this entire circuit again to implement this Clifford correction. Yeah, and you're gonna see that later on. So yeah, so this is basically the circuit that you need to do. Well, it's one way to do it, I guess. So to prepare like this ancilla that encodes this the logical gate, we do this R level concatenated code. So so basically this is yeah, so like the protocol it's still used like this concatenated code, but it's only exclusively to prepare this ancilla so that I can do universal logical gates. um so this acts as kind of like this ancilla factory, right? So I use like this concatenated code to just that, so I can get this ancilla, so I can do any gate that I want. So the idea is that, so I want to encode like this 2ni qubits, right? So because that's the like this two blocks of ancilla, right? Like this guy. um so I want to encode this qubits in like this R level of concatenated codes. I could use like like some Steam code or whatever. Um and then I want to implement um this identity tensor U bar inside this encoded like logically in this concatenated code basically. So we're kind of like just using this result from this concatenated code fault-tolerant quantum computing to implement this identity tensor U bar. Um, so now I can just decode and then get this the ancilla that I want at the end of that circuit. But what we need to pay for this is that now we have this polylog overhead from the concatenated code implementation. But that later on, I'll show you that it turns out that it's fine because basically we do like because based and that is because we do like this sequential circuit, so we only need like to do we only need to do this on like a single gate at a time, because that's kind of like what we do in this protocol. um yeah, so that's basically it. So if I choose this m to be polylog of k, so this is number of of the blocks that I use of the LDPC codes. So yeah, so we need this ki to be k over polylog k, and ni to be grow as k. Um, then we only need to kind of like do this, right? So if I plug this in as ni in there, and I'm gonna get this ki, but ki is just k over polylog k, right? And the thing inside here is also like k polylog k. Um, so it's just um, the order of k, right? And then so that means like if I take the overhead formula, so I have this O of k over k, and then I still have a constant. Um, yeah, so that's basically what I told you before. Yeah, so if U is a Clifford, then yeah, this correction is just a Pauli. But if it's a non-Clifford, so if I do a T gate, if I want to do a logical T gate, then if this is it's this T bar P A T T bar dagger, then this guy's gonna be in the second Clifford hierarchy. So it's a logical Clifford. Then I need to prepare this ancilla for this Clifford correction if I need to do a correction, and we need to take that into account later on. Um, uh, yeah, so for yeah, okay, so if I want to prepare like a logical state, like for example, like in the very beginning of the circuit, then I do the concatenated code ancilla factory again. And for measurement, if it's a CSS code, then it's kind of like just transversal because you're guaranteed to always have like Z type and X type um, um, stabilizers or logical operators. Yeah, so that's just going to be a constant time. But okay, so if if it's a general stabilizer code, then we kind of like need to do like this concatenated procedure again. But yeah, I'm not gonna go into that. I'm just gonna assume everything's a it's a CSS code. Okay, so okay, so remember like last time we still need to analyze this initial error rate, right? So because we have like this p tilde and we have PD, the data error, and PB, which is the syndrome bit flip error, but we haven't looked into this p tilde. So p tilde could come from if the decoding from the previous error correction round fails, and that happens with this oh no, like if there are like residual errors actually, um, so we're guaranteed to have like this stochastic local stochastic error rate if the previous QC round does not fail. And then we're gonna take into account the errors from this logical gate implementation from this teleportation procedure that I've just told you about. Yeah, so this is one of the assumptions that we kind of like the require what we require from our code. So so the rate is going to be that if the QEC fails, and the QEC fails with um um oh no, the QEC not fail with this probability, sorry. So the failure rate of the QEC is that. Um so yeah, so now we want to look at this teleportation implementation for logical gates. Um, so if okay, so if we I think I have like something more detailed in the next slide. Oh no, never mind. Yeah, so if this capital B is kind of like um, depends on the circuit, like this concatenated code circuit that I used to produce this ancilla. And BP is the error rate of the like this ancilla. So I'm just gonna like I'm just defining this error rate here. So this is the definition. Um, and then like for the rest of this teleportation circuit, I'm going to have this Hadamard in each qubit, C naught for each qubit, measurement at each qubit, and a logical Pauli correction as well. So that's gonna be an error rate of 4p probability of failure of qubit error, right? Because each qubit is um, involved in this four different operations. Um, yeah, so we just putting things together. Like assuming like the previous QC cycle does not fail. So we're gonna have this um, um, residual error probability. And there's a two in front of it because like if we want to implement a C naught between across two different blocks, I need to do like the teleportation on like like this other block like this NIKI. So we have this first error rate. Um, and the second one comes from error rates from preparing this ancilla. And then the rest of these are from like this gates in the rest of the teleportation circuit. And that's for Clifford. But for non-Clifford, I might need to do this teleportation protocol couple times because like if I need to do a correction here, like in this green box, so I need to do that again. So I have like this additional factor of two in front of this like this five terms. And okay, so and we want these all of these to be below some threshold P0 um for the initial error rate. Right, okay. So these are what we have so far. Um, so we have this bounce on the initial error rates. So we have these two guys because we have like this Clifford and non-Clifford bounce, and we have the data error bound and the syndrome error bound. So now what we want is that we want this overall threshold that bounds um, there was a local stochastic error rate P with this PT, and we want um, all of these four inequalities to be satisfied whenever P less than PT. So we want PT that's find a PT that satisfies that. Yeah, that's what we're gonna talk about next. So okay, so I'm just gonna restate this like show you again like this threshold theorem. So okay, so far we've gone through like all these stuff. Um and then now we want to kind of like look into like this threshold. Um and then like this P is less than PT and then kind of like show that this C tilde only uses at most like this eta K over R physical qubits. So R is the code rate. Um, yeah, and we want to choose like some of these kind of like funky numbers like this alphas and betas, which going to kind of like correspond to like how big your circuit is with respect to the rate of logical errors caused by failure in QC cycle, which is this function G. Um, yeah, and we want to show that um, this this distance of outputs from circuit of circuit C tilde from NC is bounded by this epsilon. Um, yeah, and then later on we're gonna go through like this other overheads like locations and classical computation. Right. So yeah, so we're gonna start from like this logical error probability to be at most some non positive number epsilon. So okay, so this original circuit C have f of k locations. So we need like the logical error rate per logical location to be smaller than this. Um, so okay, so if this epsilon zero is an ancilla preparation failure, um, then we need this epsilon zero to be smaller than this epsilon over 3fk. And the reason we have 3 here is because I might need to prepare two ancillas, like that teleportation ancillas. um, if I want to implement a T gate, for example. Um, and we have this probability of D over GNI of the QEC cycle fail. Um, that the QEC cycle failed. Then so I want to choose I such that like this is like this kind of like error is also smaller than this epsilon over 3fk. So I can just take I such um, like sufficiently large I such that this n case larger than k alpha. Um, yeah, because like we had like this assumption, one assumption um, from the theorem, which we can use. Um, so basically, what we want to do here is that the probability of L logical locations failing is going to be bounded by either like like this first bit, like this ancilla preparation, or failure QC failure at that location. Yeah, and we just take these two numbers. So at the end we get this epsilon over fk. Um, and basically here like we kind of like use this these two inequalities. Yeah, so that's what we got from the last slide. So and then we just put everything together, like because now we know the probability of some particular location failing, or we have an upper bound for that. So the probability of some failure is we can just use the union bound, and then like just upper bound using what we got from the previous slide. Um, so now we can get this probability of failure upper bounded by this epsilon. Um, yeah, so that means if I have like like this ideal output probability and noisy output probability, like probably with logical errors. Um, so this is kind of like the failure probability, right? Like so the probability of a noisy computation is just this probabilistic mixture between the ideal one and the noisy one. And then you can show that the total variation distance between these two distributions, the ideal one and the noisy one, is just epsilon. Okay, so we took care of the errors, and now we want to look at the overhead, and we want to show that it is actually constant as claimed. Um, right. So all the physical qubits that we have are either data qubits or ancillas for QECs or ancillas for either gates or preparations or measurements. Basically like any logical operations. So first we want to look at the data qubits. Um, so this is kind of like what we get. And that's basically from observing the number of blocks that we use and taking a large I such that like this the rate of the code that we're using is very close to the encoding rate, to the asymptotic encoding rate. Um, and then like because we use m blocks and each block has ni physical qubits, so the total number of data qubits is just m times ni, and we want to bound that with this with some for some omega larger than zero. Okay, so now we want to bound this ancillus for the QEC cycles. So yeah, so at any given time, we do most the most number of QEC that we do is on M by S blocks, um, right? Because like we further partition this M blocks into M over S partitions, to S partitions. So in each partition, I'm gonna have M over S blocks, and I'm only gonna do QEC on that partition, and I'm just gonna, go traverse through them. Um, so yeah, so to take the total to make the total number of QC ancillas to be small, I want to take a large S. Um, and yeah, so we have this R prime. That's the total number of ancilla qubits per cat state. So that's kind of like constant, um, because we're using LDPC code. And I have this 1 over AP because we're doing this post selection on preparing this cat state. Um, yeah, so that's kind of like what we have. The number of ancilla qubits for QECs, right? So because Ni minus Ki is the number of generators, MS is the number of QECs that I'm going to be doing in parallel, and I'm going to divide that by 1 minus AP because I'm doing this post selection on preparing the cat state. Okay, so now lastly, we have this the number of qubits for ancillas for gate teleportation, and that's denoted by this n up. So we have this because we're using this concatenated code. So we need to use like this polylog number of qubits in this for this concatenated code encoding. Since we assume our circuit to be sequential, so we only gonna do like at most one um, logical operation at a time. So yes, just gonna be this polylog overhead at any given time. But yeah, we need to later on we need to pick this ni such that we can bound this to be constant in a in k. Sorry. Okay, so yeah, we're just putting things together from what we got from the last slide. So we want to pick this eta greater than 0, such that like the total number of qubit is kind of like constant, upper bounded by like this O of k basically, and the constant is this eta over r, right? So that's kind of like the multiplicative constant of this of the overhead. Yeah, but now we kind of still want to pick, like this, because now we have this bunch of inequalities that needs to be satisfied for this to happen, right? For this constant overhead to happen. So we need to pick like, this omegas and lambdas and mu's, and we need to kind of like um pick like, this ni as well. Okay. So the first two is quite simple. So yeah, we just need to set m to be smaller than this number. And then we can just plug that in. And we pick a large S for this. Um, and we use this yeah, we pick ki and ni such that this is satisfied. So now, yeah, you can just plug in ni in there, and then you get this first inequality. Um, and then you do the same thing, get the second one. So, but yeah, I'm not gonna go through like step by step here, but that's basically what you want to do here. Um, yeah, and then like for the two last inequalities, so this is basically to ensure that the logical error is sufficiently low after decoding for each QC cycle, and the overhead for implementing this gate teleportation is also low, which is this um, inequality. Okay, so what we want to do here is I pick the smallest I such that ni is larger than k to the alpha. Um, and yeah, by using that um, uh, for the this first inequality, basically I can just show that this is true. And then like for this second inequality for the logical gate overhead, I want to pick ni to be smaller than this number, and that's going to just magically work if I plug this into like to this right side of so to this side of equation 11 by doing some like some algebra. So this is part of it. Um, yeah, I there was like couple more lines here that I don't show you. But yeah, basically, um, uh, if I use this ni, I can bound this term, by this and by just for some t greater than zero, and that's going to work, just fine because now it's kind of like a constant in k. Okay, so the reason why this ni exists is because it's kind of like embedded in the assumption that we have in the threshold theorem, which is this growth, of this for ni minus one to the next ni. So it's growing, as that. Um, and that's probably like that's basically just going to work for our construction. Because like yeah, so um, because we're picking like the smallest I such that ni is greater than k alpha. So that means, this is true um, from this, yeah, because like this is the smallest I such that is that this inequality holds. So then I can just use this relation, and then just show that everything works out fine, and I can get this ni that lies between this k alpha and this this crazy looking number, which is basically um, what I need, right? I need this guy, and this equation 12 here. So basically, there exists such an I. That's what I'm trying to show here. Okay, so now we want to okay, I'm really running out of time. Um, yeah, I don't have much left. But yeah, I'm just gonna rush a little bit through this, I guess. Um, so here what we want is we want to count the number of logic of locations of physical locations for QECs. Um, so we need to take into account the weights, right? Because we're cycling between blocks when we're doing QEC and cat state preparation for all this Ni minus Ki stabilizers. Um, and it's using this number of gates for preparations and to our gates for like the actual teleportation. Um, or sorry, not teleportation, like just this like the C knots and Hadamard's just to measure the syndromes. So yeah, if we just put them together, so for every QEC cycle, okay, and yeah, I repeat the syndrome extraction. So we have this T of Ni, And yeah, just put all of those together and get this equation 11. So the number of actual physical locations for every QC cycle is this equation 14. Um, and then, I do like M over S QECs in parallel at any given time. Well, between gates anyway. Um, so the number of locations that I use is that, I just multiply this M over S to this right-hand side of this equation 14. Um, and it turns out to be just that, if I just use like big O notation. Yeah, so if t is polynomial, then just this just O of some polynomial. Right. So now our logical gates. Um, yeah, so between logical gates, we have like this QC cycle, so we use what we got from this, right? So that's the reason why we have this first bit. But we also have like this concatenated code circuit. So we have this polylog overhead. Um, yeah, and I can substitute. So this should be polylog in Ni, but I can substitute in like this K by like using like this relation that we established in a couple slides back. Um, and that's gonna give us an upper bound on number of physical location for every logical location, right? And then if you remember, we have okay, I should have written down that here. So the original circuit C have f to the k, f of k locations, right? So the total number of physical location in this circuit C tilde is just I just multiply f of k to this right hand side of this equation 15. And yeah, I use kind of like a substitute in case for NIs from what we have established in the previous slides. So now yeah, so this is bounded by this big function of k, right? Um, so if the location overhead is basically just this bit, so it's kind of like polynomial in K, right? If you can, because this T, that's the number of times you repeat the syndrome extraction. That's just a polynomial. And Fk is the size of the original circuit. So basically, this is a polynomial location overhead. And there is still this classical decoding. So yeah, so basically, I'm just gonna skip the result. Um, so this is if each decoding runs in this OHN time, it's basically h of some polynomial of k, polynomial in k. Um, yeah, so if h is polynomial, then this is still a polynomial in k, which is fine. So like in total, it's gonna be polynomial overhead. Um, yeah, so we just showed that. Just a couple of quick remarks. So there's an instantiation of this protocol using expander code, and they showed like that they have this single shot decoder, so you can just do one syndrome extraction, and then decoder runs in log ki time, which is kind of nice. And then there's another further improvements by Nguyen and Patterson. So they only use constant time classical computation per logical time step. Um, yeah, and they improve this to be only log time overhead. So just constant time with constant space overhead and logarithmic time overhead. Yeah, so I just want to mention that. And that's pretty much it. Um, Thanks.
Yeah, thanks, Andrew.
Uh-huh.
Uh, so thanks, like uh, If anyone has any question, maybe please unmute yourself and ask.
Hi. Yeah, thanks. Um, so you went
Mhm.
through the Canal gate teleportation protocol, right? And
Uh-huh.
if you need to implement something from a certain level of the Clifford hierarchy, then the correction falls in the like, next lower level, right?
Eh,
Uh,
the
right?
correction is, yeah.
Yeah, yeah.
Yep.
So you could, so in principle, you could have, say, a universal gate set consisting of Clifford plus something from just the third level, right?
Yep.
Like T.
Yep.
Uh, but you could also, if for some reason at some point in your circuit you needed to implement something from a much higher level, right? You
Hmm.
could either decompose that into this Clifford plus, T or something, or you could just do nested teleportations. Is that a trade-off, or is it always obvious that you want to do just decompose it into T gates and just do gate teleportations for T, or like whatever from the third level?
Um, Sorry, so your question is whether I want to implement like some like this lumped up if I have like C knots and Hadamarts and I just lumped all those up to this U bar, or I want to decompose them one by one. Is that what
No,
you're
no.
asking?
So if I want, let's say, something from the fourth level,
Ah,
right?
okay.
I could either decompose that thing into Clifford plus stuff from the third level, right? And then, I mean, let's take T as the non-Clifford gate. And then for each T, you do this gate teleportation,
Ah,
or you
I
do
see.
nested teleportation, just directly to
I
get
see.
that thing on the fourth level. Is that an interesting trade-off, or is it, is there some obvious reason why, you should always just decompose it into the third level stuff?
All right. Yeah, I'm not sure. I guess okay, so I guess that will depend on what's okay, so if I take some U bar from the fourth level and how I can decompose, like what's the minimal decomposition of that U bar to like Clifford's in the third and second level. So if that's not too bad, then um yeah, so I guess like that's kind of like the consideration, like so how many level 2 and level 3 gates that you can decompose from that fourth level U bar compared to just like preparing this ancilla U bar and then just deal with correcting using third level and then probably like second level and so on. um yeah, I don't have like a clear cut answer, but yeah, I guess that will
Makes
depend
sense.
on like the decomposition.
Okay, thank you.
Mhm.
Yeah, any other further question? Uh, if not, this concludes our 18 session long tutorial series. Thanks, Andrew, and thanks everyone who talked, and also to the audience. We will take a break and we will see when to resume our regular seminars. So let me stop the recording.
Thank you.